topic of a video will be method of separation of variables that can be used to solve a heat equation and wave equation, right? That will be part of our next videos. So what is this method? Method of separation of variables. How it works, right? Let me give a small brief for it. You are given a PDE with U, right, with a dependent variable U, say, right, and independent variables X and T, say, right. So I have taken only two independent variables. However, this method can be extended to n independent variables, right? And you have a dependent variable which is a small u. Okay. Then the method says that assume the solution u as a product of two functions like capital X and capital T function of T, right? Means you will be assuming the solution of this form, that is product of two functions. One is a pure function of X, right, and the another is the pure function of T, right? If there are more independent variables, then this solution can be extended, right? That is u x x x and t t and p p and so on, right? I am giving the theory for only two independent variables, right? So the method says that you just plug in this u in your differential equation, given differential equation, right? Assume this and plug in it the given PDE, right, to get two ODEs, to get two ordinary equations, right, in XX and TT separately. And this is the most important part of this method. When you plug in this u, there is a product of two pure functions in your PDE, right? Then you will be getting two ordinary differential equations, one in X and other in capital T. Then you will be allowing to use the techniques that are used to solve ordinary differential equation. Then you can obtain capital X and capital T in terms of small x and in terms of small t, right? And after getting capital X and capital T, you will put those functions here and that will be your solution, right? So this is the method of separation of variables, right? And it has some limitations, and the reason is still not known that when this method can be used, right? But at the moment I can tell you that this method can be used when the given PDE is a linear one, right? Linear, what do we mean by linear? Linear means every derivative, the degree of every derivative term should be equal to 1, right? And as long as the coefficient of the derivatives are constants, right, then you can use this method. Okay. So the sufficient condition to use this method is that the PDE should be linear and should have constant coefficients. Then you can use this method, right? And in case of non-linear equations, or when the coefficients are some functions of x and y, still this method can be, may or may not be used, right? So there is no strong theorem which tells you that when this method of separation of variables can be applied, right? But a sufficient condition is that in case the PDE is a linear one and has constant coefficients, then you can use this method and this method works, right? Okay. Yeah, and there is one condition on the domain also. If you think the PDE with a domain, right? If you think it geometrically, right? Whenever a PD is given with a symmetric domain means a domain of a kind of this board, right, rectangular domain, then this method works, right? For non-symmetrical domain, this method doesn't work. Okay, we will be seeing this in our next video when we will be solving heat equation and wave equation, where this domain will come into play. Then this method will work there, right? Okay, so in this video you can think like that. The PDE should be linear and it should have constant coefficient, then this method always work, right? Okay, so taking my first example, that is example number 1. Let me take ux. Ux means u is the dependent variable and x is an independent variable, and that is obviously del u over del x, right? You may like it to write in this way, del u over del x, right, is equal to 2 times del u over del t plus u, right? You can see that u is the dependent variable and the independent variables are x and t, right? And the initial condition with ux comma 0, ux comma 0 means the value of x is x for all values of x, and at t is equal to 0, right? The function is given by 6 times e to the power minus of 3x, right? Since u is a function of x and t, so it is obvious to write it as this way, u x comma t. When t is equal to 0, the function takes this value 6 times of e to the power minus 3x, right? And you can see that this PDE is obviously a linear PDE, right? Since every derivative is having the degree 1, right? And the coefficients are the constant coefficients. The coefficient is 1. Here we have 2, right? So you can solve it by this method of separation of variables. There is a sufficient condition to use this method, right? Okay. Now solution. Let me start with this one. Let u is equal to capital X, by writing this way, I mean capital X is a function of x alone, multiplied by capital T, which should be a function of t alone, right? Okay. Then finding del u by del x, right? Finding del u by del x will produce del u by del x will produce the differentiation of this function, because this is a function of t, that will produce t times, now I am skipping this term inside bracket, okay, capital T of t obviously, and del x by del x, let me write that x dash, right, where x dash means del x by del x, and that is eventually the same as ordinary derivative. You can see that, right, because since it is a function of x, right, so the partial derivative will be equal to the ordinary derivative, right? Okay, and del u over del t will be x times t dash, where t dash is equal to del t over del t. Since t is a function of t only, x is not involved here, so the partial derivative will be equal to the ordinary derivative, dt by dt. Okay, fine. Let me put these values here in a given PDE. Then plugging these values here, I will get t x dash equal to 2 times x t dash plus x t, right? Okay, and let me try to separate, because see this, plug it in the given PDE to get 2 ordinary differential equations, right? My aim is to obtain 2 ODEs from this single equation, right? And 2 ODEs means one in variable x and the other in variable t. So that should be your target. Try to separate it in that way that t and x get on different sides, right? Let me divide this by capital XT. Divide by xt, right? Okay, then it will be x dash over x equal to 2 t dash over t plus 1, right? And now you can see that the left hand side is a function of x and the right hand side is a function of t, right? And let me assume these two ratios equal to some constant k, say, right? And why I have taken these two ratios equal to some constant, the reason is that because the left hand side, this will be a function of x, right? Because as I have said that capital X is a function of x only and capital T is a function of t only. So the left hand side should be a function of x only, the right hand side should be a function of t only, and if the two functions are equal, they can only be equal if both of them are some constant, right? So precisely the left hand side is a constant, right hand side ratio is also constant, and that should be equal to k. Okay, now let me try to make two ordinary differential equations from this system, right? One will be given by taking the first ratio equal to k, and the second ODE will be given by the second ratio, taking second ratio equal to k. Okay, this will give, this gives capital X dash minus k x equal to 0. If you cross multiply this capital X with this k and take this term on the left hand side, then this will be your ODE, right? Okay, and 2 t dash over t plus 1 equal to k will give you that should give you I think divided by tk 2t dash minus tk 2t dash minus kt and plus t, k minus 1 minus k plus 1 minus k t equal to 0, right? Or you may write it as by 2. Okay, right? So one is the ODE in x and another is the ODE in t. You can solve them. The solution of this will be given by let me write it here, implies for this the solution will be capital X as a function of x is equal to constant and e to the power k x will be the solution, right? You can solve it very easily. This is a variable separable form. X dash over x is equal to k, then integrating on both sides will be getting a solution like this, right? Okay, and on solving this I will be getting, and t as a function of t I will be getting, I think capital B is the constant of integration, e to the power k minus 1 by 2 small t, right? Where a and b are arbitrary constants, right? Now as I have got capital Xx and capital T of t, both functions, I can plug them in this solution. U is equal to capital X multiplied by capital T, and that will be my solution, right? Therefore U, now U is a function of x and t, remember that, so you should write it precisely. U a function of x and t, capital Xx multiplied by capital T, put the values here, capital A e to the power kx multiplied by capital B e to the power k minus 1 by 2 and t, right? And see that A is a constant, B is a constant, multiplying two constant will produce another constant that will be capital C. Let me write it capital C, and e to the power kx e to the power k minus 1 by 2 t, where C is a new constant, that is the product of two previous constants A and B. Okay, so this is my solution. Now I will try to impose this condition on this in order to get this C. Okay, Now using this condition on this solution, okay, let me put a box here because this is our general solution containing the arbitrary constant. Now use, since u x comma 0 is equal to 6 times e to the power minus 3x, right? Use this condition, initial condition. Why I am calling it as initial condition? Because here the t is equal to 0 and small t is generally denoted by for time, right? And if time is 0, then that should be the initial condition. Okay, so for t is equal to 0, I have this condition, so I should put t is equal to 0 here, and we'll be comparing this solution with this condition, right? So putting here u x comma 0, put x in place of x, and in place of t equal to 0, I will be getting c times of e to the power kx, implies c times e to the power kx, because e to the power 0 will become 1, okay, and the right hand side is 6 times e to the power minus 3x. Then you can compare both sides. C is equal to 6 and k is equal to minus 3. On comparing both sides, the power of exponential function and the constants, right? And then after getting c is equal to 6 and k equal to minus 3, plug these constants here to get the full solution. Then u as a function of x and t is equal to 6 times e to the power 3x and e to the power 3 minus 1 by 2, that will be 2 by 2 t, or you can write it as e to the power 3x plus t is the solution, right? K is equal to minus 3, sorry, minus 3, and putting minus 3 here will produce minus 4, minus 2t, and that will become minus 3x minus 2t. Fine. Okay, so this is the required solution, and you can see that we were given a PDE that was luckily linear PDE and the coefficients were constants, right? And then we start with this, with the solution of this form. This is the product of two functions, pure functions. One was a function of small x and one was a function of small t, right? And then after plugging this solution here, I got two ordinary differential equations, this one and this one, which I was able to solve them, right? I solved this to get capital X, solve this to get capital T, and then substituted these functions here to get the full solution, right? And after that, this initial condition comes into play. Then I found the constants also. So this is my final solution, right? So taking another example, example number 2. Let me take 4 del u over del t plus del u over del x is equal to, and let me take right hand side is equal to some function of u, dependent variable itself, 3u, with the initial condition as in our last question I took ux0 is equal to 6 times e to the power minus 3x, but this time I will be taking some more complicated initial condition, and that should be u x comma 0 is equal to 3 times e to the power minus x, and let me take another function, exponential function again, and e to the power minus 5x. So you can see that this time the initial condition gets extended, right? Okay, and let me start the solution, and let u is equal to capital X as a function of x and capital T as a function of t, then doing those partial derivatives, you know that, and then putting these here, I will be getting, should I write it directly? Okay, then after finding the derivatives and plugging them here, I will be getting, this gives me the 4 times del u by del t means x t dash plus del u by del x means x dash t is equal to 3 x t, where I should mention that x dash is equal to dx upon dx, and I have written the ordinary derivative because the partial derivative is equal to ordinary derivative, right, here in this case, and t dash is equal to dt by dt. Okay, then dividing it by, divide by xt. I will get here 4t dash over t plus x dash over x is equal to 3, right? And try to separate them in order to get x on one side and t on other side. I will be getting 4t dash or 3 by 4, okay, 4t dash is fine, or divided by 4 also, 4xt, but that will produce 4 here, no, leave it, 4t dash over t and minus 3 equal to minus x dash upon x, right? So you can see that the left hand side is of t and the right hand side is for x, and since these are ratios and that should be equal to some constant, you know the reason why we are taking it as a constant, not a function. Okay, then this will give rise to two ordinary differential equation, one in x and the other in t. This gives two ordinary differential equations, one in t that will be taken this, okay, that will be 4t dash and that will be kt, and that will appear here minus k plus 3 times t is equal to 0. I think this is fine. Okay, let me take this 4 here. Okay, now it's fine, right? That will be kt minus kt. Okay, correct. And the other will be positive x dash plus kx equal to 0, right? Okay. Now solving these two, you can solve them easily. This is the first order ordinary differential equation, and obviously that is variable separable. You should write it as dt over dt, this value, and then taking the capital T on one side and small t on the other side, and integration, performing integration, then you will get a solution as the solution for this will be t as a function of t is equal to some constant times e to the power k plus 3 4 times small t. So this should be the solution. And for this one, capital X as a function of x is equal to capital B times e to the power minus kx will be the solution, right? You can verify them. And where a and b are constants, where capital A and capital B are arbitrary constants. Okay, fine. So after finding capital T and capital X, I should substitute these functions in my solution. Then u as a function of xt, right, should be equal to the value of capital X, and that is this one, capital B times e to the power minus kx, and the value of capital T, that is capital A times e to the power k plus 3 by 4, and here I have t, right? And obviously the product of two constant will be a new constant. I am writing that constant in this step only, that should be equal to a new constant c, and here I will mention my c is actually equal to capital B, new constant. This is my solution, right? But it is containing arbitrary constants c and k, right? And notice that this k is called separation constant, right? Separation constant. Okay, then use this condition here. Since u x comma 0 is equal to 3 times e to the power minus x minus 5 minus e to the power minus 5x, means that for t is equal to 0, the function takes this value, and substitute the t is equal to 0 here, then this will give, this implies that 3 times e to the power minus x minus e times e to the power minus 5x is equal to c times e to the power minus kx. And see this, if you put t is equal to 0, this will become 1, right? And I will be left only with this term c times e to the power minus kx, right? And this is the important step. Note that c is an arbitrary constant, and k is also a separation constant, that is also arbitrary constant, and you may vary c and k, right, according to this left hand side, right? So let me write it as c1 k1, right, and another solution c2 e to the power minus k2, and please notice this step, right? Why I have taken plus here, because as we are dealing with the linear equation, and we know that the solution, two solutions, right, the sum of two solutions is again a solution, right, the sum of any number of solutions is again a solution, and that is the idea behind this, right. And I know that this C is an arbitrary constant, whether it is C1, C2, C3, C4, whether it is K1, K2, K3, K4, they all are solutions, and this sum is also a solution. That is also called a superposition principle, okay. And in order to compare them, in order to get this C's and K's, I have to write this solution in this form, right. And moreover, if the initial condition would have contained three functions, 1, 2, and another function, third function, then I have to write C1, C2, and C3 and e to the power minus K3x in order to compare them, right. And now you can compare, okay. See this e to the power minus x, right, and so this should be compared with this one, okay. This gives on comparison, right, C1 is equal to 3 together with the K1 is equal to 1 if you compare the first term, right, and this is a pair, C1 3, then K1 is precisely 1, right. And the other comparison will give you C2 is equal to minus 1, C2 is equal to minus 1, and K2 is equal to 5, right. And you cannot switch these C's and K's. If C1 is 3, then K1 is 1 fixed. With C2 equal to minus 1, K2 is equal to 5 fixed, right. Means as a pair of C and K, they are fixed, right, okay. Therefore, the solution will take the form, see this, C times of this thing, C times of e to the minus kx, right, but I have got two C's and two K's, so I have to write the solution as a linear combination of two solutions, one in C1 K1 and the another in C1 K2, right, okay. The first solution will be C1 e to the power minus K1x e to the power K1 plus 3 by 4 t, and the other will be C2 e to the power minus K2x e to the power K2 plus 3 by 4 t, right. And after writing them in this way, substitute these C's and K's, and that will produce ux comma t, that will produce 3 times e to the power minus x, and this will give you e to the power t, right, 3 plus 1 4 t. So should I write it at plus t? Okay, fine. And here minus 1, okay, e to the power K2 is 5, e to the power minus 5x, and here it will be 5 plus 3, 8 by a, okay, 2t plus 2t plus 2t, fine, is the solution, right. And you can see that you can verify that this is correct by putting t is equal to 0 here. If you put t is equal to 0 in the solution, you will get 3 times e to the power minus x minus e times e to the power minus 5x, and that is eventually the same that was given as the initial condition. You can match this function from here, right. So this is my second example, and taking our last example, example number 3. Now taking example number 3, that should contain some mixed derivative. So far I have done 2 examples in which both were containing the pure derivatives ux and ut, but this time I will be taking an example which is containing the mixed derivative, and let me take it the mixed derivative as uxt, or I should write it as del square u del x del t. See, this is a mixed derivative, right, the second order mixed derivative. On the right hand side, I take some exponential function multiplied by some trigonometric function. Let me take it e to the power minus t multiplied by cos x, right. And let me introduce this time the initial conditions with 2 conditions actually. Ux comma 0 is 0. This is my first condition, and taking another condition and del u over del t 0 comma t equal to 0. This is my second condition. I have to do partial derivative with respect to t this time, okay. So again you see that this is a linear PDE, because if you see this second order mixed derivative, then the degree is 1, okay, fine, and the coefficient is also constant, right. Solution, let u as a function of small x and small t, capital X of x and capital T of t. You know that capital X is a function of x alone and capital T is a function of t alone, right? And then doing its second derivative and putting it here, this gives, if I do differentiation of this with respect to t and x, I will be getting x dash t dash is equal to e to the power minus t cos x. And let me write what is my x dash, that is dx by dx, right? And t dash is equal to dt by dt, right? And try to separate the x and t's, I will get, or x dash upon cos x is equal to e to the power minus t upon t dash, right? Fine. And let me take them equal to my separation constant, that is equal to k, say, right? Now taking the first and the third ratio, I will get the first ordinary differential equation as x dash equal to k cos x, and the second one will be t dash equal to 1 by k e to the power minus t. Okay, that is fine. And let me try to solve it. Since x dash is dx upon x, that will give me dx over k cos x dx, and on integration I will be having capital X as a function of x, integration of cos x will produce sin x, k sin x plus capital A as a constant of integration, right? And on integrating that, I will be having dt is equal to 1 over k e to the power minus t dt, and on integration it will give t as a function of t. The integration of this thing will be minus e to the power minus t by k plus b, right? We have capital A and capital B. Arbitrary constants, right? Now putting these values here, uxt, therefore u x comma t will be equal to product of two functions, right? And that will produce k sin x plus capital A multiplied by b minus e to the power minus t upon k. Fine. This is the solution, general solution. Okay. Then using the first condition, since u x comma 0 is equal to how much? 0 is given, right? Putting t is equal to 0 in this solution, I will get, implies t is equal to 0 here, I will be getting k sin x plus capital A, and t is equal to 0 will produce e to the power 0, that will be 1. So b minus 1 by k, b minus 1 by k is equal to 0, right? Now here comes the important point, that since these two product of two functions of factors is equal to 0, either this will be 0 or this will be 0, right? If you take k sin x plus capital A equal to 0, right, and then you will substitute that here, then that will produce u is equal to 0. That is a trivial solution, and we are not interested in 0 solution, we are interested in a non-trivial solution, right? So take that factor equal to 0 or allow that factor equal to 0 which don't produce a 0 solution. If you take this is equal to 0, that will produce a 0 solution here. So you have to take b minus 1 by k equal to 0, right? This implies b minus 1 upon k equal to 0, and you should know the reason why, right? Because if you take this equal to 0, that is producing a 0 solution, and that is the thing we don't want, right? And that will give me b is equal to 1 by k, or capital B is equal to 1 over k. Fine. Then my solution reduces to k sin x plus capital A multiplied by the value of b is 1 by k, and 1 by k will comes out 1 by k 1 minus e to the power minus t is my solution, right, is solution, is a refined solution, right, with some lesser number of constants. Now using that second condition, this condition, but for that I have to find del u by del t also, del u over del t, right, at x comma t. Okay. If you differentiate this with respect to t, you will be getting 0, and that will be e to the power minus t, I think, right. Okay, then you will be going to use this condition number second. Since del u over del t 0 comma t equal to 0, that will give me, implies, putting x equal to 0 here, this term will be 0, and that will produce a over k e to the power minus t equal to 0, right, and obviously this k gets multiplied here, you will getting a e to the power minus t equal to 0, and that will produce obviously capital A equal to 0, right. Okay, and writing capital A equal to 0, there is no harm to get a non-trivial solution, right. If you put A equal to 0 here, okay, that is fine, non-zero solution, right. So this is accepted, A equal to 0. This gives therefore u x comma t, my new refined solution, k times sin x, but capital A is now 0, and 1 by k times 1 minus e to the power minus t, and k will be cancelled out, or u x comma t sin x multiplied by 1 minus e to the power minus t is the solution. This is the final solution, right, and you can verify that these initial conditions satisfy this solution. If you put t is equal to 0 here, then that will go to 0, right, and after differentiating this with respect to t and putting x equal to 0, we'll get 0, fine. So you have seen that how this method of separation of variables works, and make it clear that it surely works for linear equations and with constant coefficients and with the nice domain like rectangle or circle, right, and we'll be taking this method in our next video, that is the solution of wave equation, and that the solution of wave equation is done by using this method, right. This method works there, the solution of wave equation, heat equation, or Laplace equation. We'll be doing that in our next video. For this video, thanks.